Okay, good afternoon. Thanks for being here. A couple of announcements. We have a Students' Day on the May 12th at Fraunhofer. If you are interested for the ERF, it's an overview which is given where people report what we do and so on. It's for students like you. So if you want to apply, it's going to last till next week, and it's quite done conveniently for you. So the day is actually May 12th, and the application is 1 week earlier. So if you're interested, that would be that's something you can find there. So if you just put ERF and then Students' Day, I think you will find the link. I also put it on Ilias. The other thing is we are also searching for a Hiwi. If you have some interest in RF measurements and electronics, then we are searching for somebody doing that. So this is about setting up some more advanced setups there. As you see here, this is, I think, a 220 gigahertz probe station, and we are just doing that at the chair here. So if you're interested, just contact me. Also, there's also one of my co-workers at the internet. So that's something if you just have some interest. What I'd like to do today in the lecture is that we talk a little bit about the waves and why actually they move and why they work. This is something which is important, because otherwise the whole story doesn't work. The Ilias support you have, and what I would like to be talking about is some very basic ideas. So we had a summary last time that we have the microwaves in a lot of applications, and it's strongly increasing. We are worried about the omnipresence of microwaves recently, and the special thing is the Internet of Things. So this is where we have essentially this. Sorry, it's another one blanked out. This is the Internet of Things, that we have an omnipresence of microwave connections, and in both sensing, so it's used as a sensor and also as a communication means. And maybe just also to give some ideas, when you open your cell phone, this is you're not surprised to have a Face ID. Yeah. This is presently an infrared image which is taken from your face. So this is used for your identification. It can also be done with microwaves. It's the same thing. It's just to establish that a lot of times in these things there's a lot of advancement, so it's not as conservative as given here. So there's not only the idea of to open a garage or something like that, but it's something which is increasingly available for what we do. You have loudspeakers. You're not surprised that the loudspeakers are capable of transporting the information to your ears without a cable, and this is ongoing. So there's a strong push on connections which are in the billions on this planet. So that's what's striking. What people do not know so much is that is some very basic knowledge about the atmosphere. So the first thing is that we typically think when microwaves are connected that we think in line of sight. So I'm talking to you, and you get this because you get a straight piece of information. Yeah? And this is one way of looking at it, and that is, of course, very valid. However, some more classical things are just our atmosphere. That is something I always want to explain, why we can do radio communication at all. Why does the classical broadcast radio work? Yeah? And that is not so easy to be understood, but it's actually, if you take it from the idea of there's nobody yet, but still could come somebody. If you share this idea of microwaves, then we have a waveguide, and the atmosphere we have outside there is damping, but it's also a waveguide. So that's something which I would like to mention to you. And it's very frequency dependent, so we use the top layer. The sky is a waveguide. That's a very fundamental idea. So we can talk to over the horizon to somebody because the atmosphere on the other side is reflecting. And it's frequency dependent. You see that here. In ancient times, they went through the alphabet and the D, E, F layers, just going up essentially into space. So before they ever could reach space, so this was in the 1900s. And they saw that the microwaves actually are being reflected. Yeah? So this is also a very important idea, that not just you have a direct line of sight for the microwave communication or sensing, but that you also get a reflected signal. Yeah? And this idea is important because this is, of course, quite straightforward. The same happens when what I told you last time about when we speak about very modern MIMO. Yeah, when we speak about multiple input, multiple output. Somebody joining. Let's see whether we. And the idea here is that you get through this in the atmosphere and also around buildings. So you get a connection everywhere because it's not only working as for the broadcast here, but also in the 2D around the building. So you have an indirect communication with the base station via, for example, a reflection in a wall, at a wall. Yeah? So this is why when you take this, and we have a line of sight communication at some parts to the base station, and you go around the building, you get the same effect, but not in the x-axis, in the z-axis, but also in the x and y axis. And this is why these things work at all. Yeah? And if there are multiple paths, so here in this case it's 1-to-1, so you essentially get one path. But for various types in the 2D, where we are here in the area, you get one connection left around the IMTEC building and one connection right about the IMTEC building. What the radio will do, it will take the nicer one, and if it has two signals, it will also draw information from getting the same signal twice with a different phase maybe and some difference, and use information from that. And that is an idea which is quite fundamental. You see here the very low radio bands. Hello. The very low radio bands have a frequencies which is as low as my voice, which is just talking to you. So when I'm speaking up here, I would be speaking also at 3 kilohertz on the audio, but the very low frequency bands go down to 3 kilohertz also for microwaves. So there's an overlap of acoustic waves and microwaves just in the frequency. So this is also not a problem. There is something you can also see then. There's a relation between the waveguide in its size, because you see here kilometers or hundreds of kilometers, and the wavelength of the 3 kilohertz actually extends also over kilometers. Yeah, so this is again this idea that waves are also in relation to, with their wavelengths, in relation to things which are reacting. Yeah, so that's also helpful. Yeah, so that may be. Okay. What we now do is a little bit of fundamentals. So this is something which is not historical, but it's important that you gain some knowledge about why things work technically. Yeah? And we can draw now equations down, which is the Maxwell equations, and it's and the point is, why do I mention this here? In the case of the radio, we need, for the first time, we need the Maxwell equation in their full form, with everything they have. Yeah, and when you have you been in your studies so far, there was always something crossed out. Yeah, so you got them maybe in a simplified version that maybe here you would remove the charges, or here you would simply make them symmetric by excluding the currents, which is the so this means that this first part is a simple finding that a current causes a magnetic field. That is not really surprising, yeah. And the second part says that an electric field causes again a magnetic field. But here we need both, and that's quite simple. And this is for your head now. You know conductors. Let's take one which is not connected. And you know conductors which conduct because of their physical connection. Yeah, and you know at the same time that waves can go without any conductor. So in free space we can have waves traveling because they have this interaction between the D field and the E field, the D field and the H field. Yeah? Here we are transporting waves over a conductor, because this is not just an electrical signal which we are sending through these. They are so fast that they're actually representing waves. That is the new thing which we are going to talk about today. Yeah? And this is just the names, and they are kind of symmetric, which is useful. And what is now helpful to understand some of the stuff is to take some of the properties again symmetric that we say. Typically we don't use polarization, so the polarization here for the D field, for the electric displacement, we typically disregard. And also for microwaves, the magnetization is also not used a lot in the first thing. However, even in these things, there's a lot of devices which critically rely on the fact that you have the P and the M. Yeah? So you know there's memory based on magnetization, which is attracted like that. And also we have some strong RF components which only work because you have magnetization. The way we deal with that is, however, a bit different. We first try to understand how waves would propagate, and then for this one very instant, we solve this, but only there. Yeah? So we are not considering everything at the same time, and that we will see today why there's a reason why we do that. It's because the general solution of these equations is quite problematic and also not very insightful for what we have in mind. And what the first simplification, which you have seen in the past, is the making it isotropic. So we move away from the idea that these are that there's a tensor here, so which is direction dependent properties. And the reason why we don't have to do that plastics and most of the dielectrics we use, they are quite isotropic, so they have the properties very similar in all the three directions. Yeah? And the magnetic part is not so important here, because the magnetization, apart from the few components, is just proportional. So that's not to the field. So that's not something we have to worry about at this point. Now coming to the circuit idea. So there's of course this idea that we can render a component which is an inductor, yeah, or something which is obviously electromagnetic. But what I would like to explain now, how we get this together, that we have semiconductors, which is a different story from the Maxwell equation in the field sense, and this idea that we put waves on a chip. And that is what we need, because I think the part outside the cell phone is already complicated, but that's okay. But also getting this idea that at some point the wave goes in and is still progressing as a wave. Yeah. And the other idea, which is quite nice, typically you learn this fast digital stuff from the idea of just switching currents. But you don't learn, for example, that filling a memory is essentially sending a wave package. Yeah, so when we look at this computer, we don't think that putting something in the memory is a wave action. However, it is, because it's so fast. So when you fill a memory, you essentially describe it as a current inscribed into a transistor and so on. But we are so fast by now that if you didn't consider the wave nature of the signal traveling, you would be in bad shape. It wouldn't work. Yeah? So we have to account for that. That is the closing element. And here you see this idea that we are, and here you can actually physically see that we are dealing with waves. That is quite simple. Why? Because we are connecting electronic devices, which you see here on these three. These are transistors and these are transistors, and obviously they are connected with something which is interestingly shaped. Yeah, so this is not just, for example, the output of this transistor is not a straight line going into this, but somehow somebody made some gymnastics to meander and to work out these connection lines, and this is because there's a wave transformation, and the waves are actually transported in a very defined fashion from between these 2 points, from here to here. Yeah? And now the point is, how on earth do we ever get a description about something very complex? Do we always need to account for the full wave description of simulating all the fields and everything around this circuit, or can we just understand it in a way that it's better to be caught and can also be treated in a decent fashion by you? I think that's the key, that you learn to deal with waves. That is what it's about. And there is a clear distinction here, where, and that's quite important now, the free space which we are using when we are using mobile, then we have antenna elements. This is, for example, a 4G base station. And there's obvious that there's an antenna, and there's also waves. You can see that it's like loudspeakers sending around in certain sectors. Yeah? What you have to consider, though, is that the same wave is also transported through interconnected, very small structure. And the story is that some of these structures are much smaller than the wavelength. Yeah, so once we enter that cell phone here, I told you the wavelength of the cell phone is in free air is about the size of the cell phone, so a decimeter. Yeah. When you now look into a processor, we have connected lines, and they are very small with respect to the wavelength. They're very small. Yeah. So maybe such a silicon chip is maybe maximum a few hundred micrometers, so much smaller than the wavelength. And still, the information is caught from a top level here and is transported here down there. So there we need the transport information, and also to make sure that there's really a connection. It wouldn't work if we just relied on pure conduction, because we have wave transport. Yeah? And we call that guided wave propagation. And it's very similar to this earlier image, which you had here. This is also a guided wave transport. Yeah, so the atmosphere is not just letting the wave through, but there's a guidance by the way, a question for you: why does the atmosphere reflect? What is changing towards space? Why does it reflect at all? Yeah. So there's a density reduction when we go higher in space, to the point that there's no gas density anymore at about 400 kilometers above the Earth surface. Yeah? And this particular change, apart from also certain other aspects, density, and also below it's also the forming of moisture, which also plays a role, which damps. Yeah? But there's a gradient of essentially of the gas density, and that forms a waveguide. Yeah? So this is also guided wave, but not along a conductor. Here we have, with the circuits, we are doing conduction along, we are guiding waves by putting metals. This is the idea. So the waves do not freely float over the chip. This is important. So this is the distinction. We are putting in a wave here. Yeah? And it's not going everywhere. It's going along the guidance by the waveguides. And this is a bit of a change. Yeah? So this is something you probably haven't seen, because so far you were using these connections just for transporting. Some of these lines are also used in a very classical way, just to say that very plainly, because you see that here, for example, for this line is transporting the wave to the outside, but it's also in a very conventional say just sending in parallel DC current to the transistor. So it has also in parallel a very classical function. Yeah? So this connection is not only a waveguide, but it also has, like a wire, just a second function which we need, because a transistor without normal DC current would not operate. Okay. The next thing is now, and this is also the link to the design course, there's a couple of representations rather than the actual physical alignment. So what we need always is a connection between something which we make, which is physical, and which at the same time is well represented. And the whole story about these design tools is that we have a one-to-one understanding between something we make and something what it does for in the frame of waves or signals. Yeah? And this can be quite challenging, because what you can learn now is that there's a very high degree of automation. Yeah? And for example, the top right picture is a bit stupid because it has some very old-fashioned things. Yeah? So for example, what is most critical there is just the simple bond wire. Has anybody in this room done a bond wire? So put a wire from one chip to another or something like that in any practicum, by the way. Has anybody tried that? So in some of the practica it's visible. So it's essentially you have something like a pad or some feature here on the printed circuit board, which is well defined, and suddenly we are drawing simple cables, pieces of copper or so, 100 micron, 50 micron of gold. And these are challenging because they are very much outside these classical things, these definition things, because when you make a wire, put it down, make one, then it's quite undefined. Yeah, so everybody does it a bit differently. And if anybody in this room was folding a cable, it would never be the same. Yeah? And why am I emphasizing this on the top, on the lower right? You see the layout definition of something integrated, where the definition, it can really be done one-to-one, because no matter what happens, this will always look the same. Yeah? So you're putting a component, and the electrical representation will always be the same. Yeah? While for a wire, you can understand this, that if we change the form of the wire, there's not really a one-to-one connection between the wire and the electrical behavior, because we all do it a bit different. Yeah? And the new thing is actually that we're learning to, ideally, we can simulate everything we put and back. So if we have put something and we put it also into a context, that is the next step, that for example, this chip works alone in a certain way, but we are not sure when we put it to some environment whether it does the same. So maybe I give you a strong example why I'm saying this. If you're playing a cello in free air, you expect music. Now you're putting it into a swimming pool and you don't expect it to work. And that's about what we do with packaging, because we may be changing the dielectric environment. I mean, with water, it's a bit unfair because water is strongly absorbing, damping, and killing. But what we do around this is, in a strong way, you change the dielectric environment with the PCB. And so you cannot expect a musical instrument to work in the same way, just freestanding with a nice person playing it, And if it's in a cramped environment with a lot of other things around it, that will sound differently. Yeah? And this is exactly what you do when you start this integration. Okay. So now how do we approach this? The first thing is that we're going away from the field idea for the moment. And there's a reason for that. Why we can do that is that on a schematic level, we say this thing does something. And to a certain point, it's true, because anything which is a waveguide at the end of the day will transport power from A to B. And you don't really have to know how this is done. And the only thing what you need to know is how much is coming through and so on. That's one idea. Yeah? So, and we then go, typically as human beings, we go to an impedance description, because this is straightforward. Because we are bound by Ohm's law, essentially, voltage is impedance times current. That is something we like looking at. And we make a strong differentiation here. We make a differentiation between the component and the function. Yeah? We first do it and then take it back. And the reason why we have to get it back is that once we have the function and we play with and we deduce the component again, because at some point in the layout, those in the design code have seen this already, at some point we go from a schematic level on the top back to the layout. So we want something automatically generated. Yeah? So we place, let's say, 100 transistors, and then we expect that the software will give us rules and best even automation degree, that from this, if we place 100 transistors on a schematic, we can recreate the hardware, which is layout here. The same is done here. We split the function from the component, and we say whatever the resistor is maintained by the resistive behavior, so it has the impedance of a resistor. And this we call resistance. And the same is true for the capacitor in capacitance and inductance. This is not important. It's just a split we make. Yeah? The important thing is that with these omegas here, we suddenly have the frequency of the wave. That is what helps strongly. So there we are now getting something in which from a straightforward DC representation we would not understand. Yeah? So that's where things start to ring for us. The important learning from this, however, is that a resistor is not only a resistance. And how do I know this? It's quite simple. Because we have a full view of the Maxwell equations, it's very clear that around a resistor there is also a magnetic field, which means it must have some inductance. And the same is true that also a capacitor has some resistive value, because why do I know this? Because there is some resistance here at the axis. Yeah, so anyway, we will, in general, the representation of the component will have more than one fundamental contribution. And this is not difficult, but it's important, because we are in the first order, we always say a capacitor is a capacitance, yes, but at some point we need to be more specific, because we cannot discard the behavior of the waves. Yeah, so that's why we do this. Okay, and then we are starting, this is now a very simple idea, that we are starting to represent individual components by what they are doing. Yeah? And for those components, it's quite obvious. Hopefully a resistor has a resistance in the representation on the lower side. And the capacitor also, as I said, has some inductance, because it's connected. So it means it has connection. And there's also, for any capacitor, there's also a leakage. And if there's some leakage in DC flowing, even if it's femtoampere, we will still attribute a resistance with it, because it might change in some frequency ranges the behavior. Yeah? So these are things you only learn if things start to go wrong and the model didn't work. that you're starting to think about these effects. Yeah? So it's learning, essentially. The same is true here for the inductor, which also is slightly capacitive. And you can also do RF from the intuition, and this sometimes is even a bit misleading. Yeah? So for example, you have seen in your school life, you have seen something like RF is always considered parasitic. However, this is nonsense, because it's not a parasitic effect. If you come from the low frequency regime, yes, but fundamentally you always have these effects. And for example, as you saw, the microwaves go down to 3 kilohertz, and so we have the full story also at 3 kilohertz. So it's not parasitic, it's actually quite fundamental. The other thing is also, for example, that some things are misleading. For example, we also consider radiation effects, for example, and that is also quite interesting when you have, for example, an open cable, whether it forms an antenna. Yeah? So whether would this radiate if we send a wave here to this and I would point to you, would this come out? And most of the times it would not, because this is in principle not a very good radiation characteristics. Yeah? So for example, when you have a board and the amount of energy which is effectively radiated from an electronic board is quite low. There's always a little bit, but you have to make it deliberately radiating to make sure that you really get an antenna. That's also an idea. So these radiation effects, when I think, does this radiate or not, I'm typically wrong, because my assumptions are never good. So that's something you have to investigate. Yeah? Let's go through the electromagnetics. There's a couple of things which we will use in this derivation. It's not rocket science, it's just there's two factors how to cut these derivations a bit short. And these are two vector things that we can put divergence and curls into, for example, Cartesian coordinates, which is not really helpful because this already on the right side looks very ugly. Yeah, so we don't want to use that. So we stay on the left side just to use some rules. And one rule which we will use is we need if you use these two vector operators, divergence on them, most of the things cancel out. And that's a good way, because then things get a lot easier mathematically. Yeah? I already pointed to the fact that when we do this, there is this, for the RF effect, we always want to use both. Yeah, so in your school time, it was always a current was causing a magnetic field and then also some electric field. The point is we are using both here. We need them both, because otherwise we would not understand why a connector would send a DC path and at the same time also be able to be a waveguide. That's what we need here. And this is also something which your physics teacher might not have told you, is that it's a simple coaxial cable, because the coaxial cable, which is parts in here, is a classical waveguide. It's not a classical cable. Yeah? So and this is mostly using the right side, but it also includes something like this. So there's a mix, but it's mainly wave propagation. Yeah? Okay, let's go to the derivation. We will just not look at the. So when you have now the Maxwell equation, we will cut them down, and let's start understanding this. So why do waves propagate through something like that? That is my question now. And let's start with free space. And the trick is, as engineers, we are always smart how we look at things. So we don't take the most complicated way of looking at things, but we learn something. And one thing we want from these is, that is something which I want to say up front. How, when you look at this, when you transport waves with the cell phone, what is the wavelength we are using? we said decimeters, yeah, so 10 centimeters. At what distance do you use this minimum in terms of the wavelength? So do you, for example, do you use it close to something at a distance from the of a wavelength? No, obviously not. So the idea is, and this is fundamental, and that helps you to understand why we are doing it this way. So apparently this thing is made that the waves propagate many times the wavelength before we use it. This is important because this implies something. And this implies that whatever we organize is relatively little in attenuation. Yeah, so apparently with this I can at least call you up there, which is already multiples of the wavelengths, but you would be confident that we would get a connection. It wouldn't be direct anyway, it would be over much more, but just as an idea, this is important. Yeah? And what we always start with, I told you we are doing this symmetrically, but we exclude the waveguides for the moment. Yeah? So what you normally did is you were cutting out everything which had the conductors and had the vacuum. We only looked at vacuum because it's nice for analysis. Yeah? And then you're coming down to the relatively simple symmetric equation because you're seeing they're getting fully symmetric. And there's one learning which I want first before we go back to re-including them. Yeah? We use also these vector operators, and only if you don't trust these relations, it's sometimes wise to see that when you plot them in coordinates that these relations are worthwhile. And the reason is if you put a double curl, so to say, to a field, you can rewrite this in this way. This is helpful. It's just if you put it in coordinates, it will rule out. It's just you can check for one coordinate and you trust the rest. This is not rocket science, but it's general. So it's helpful. So we only need these. We don't need to write all that. And there's another trick is that when we have the time dependence, which we will need, is we can simply exchange the differentiation in time and space likewise. So this can be mixed, and that's also another form which we need. So let's apply these two tricks to the equations, and when you then you get the divergence of E and B symmetrically, and you then apply the second trick to these two. So you put them in here and put a double curl to both sides and then exchange. Yeah? And what you get is that you're ending up, because the divergences of E and B are zero, you come surprisingly to a relatively simple wave propagation in free space. So that's a wave equation because you have a double derivative both in space and time. You're not fundamentally surprised because I think you have seen this in one way or the other. However, there's a couple of things which we can learn from that already at this point. And one nature of this is that you have a special case of a transversal electromagnetic wave. Because with this equation, you get an example of a wave which has essentially the two fields which are involved, E and B, they are orthogonal, and they are also orthogonal to the wave, the direction of propagation. This is easy for us because we like thinking this way. What you learn by that, however, is that this is not the only way which could happen in this case. So there's more solutions where you have E and B fit like that, and they are orthogonal to this direction. This is not the only one. This is a very special case, by the way. But the concept of having an E and an H field, and then something else in the direction of propagation, that is a very fundamental idea. And you have always learned that electromagnetic waves are always transversal, so they're always like that. And I have to tell you something now that your teachers lied to you. It's not true. There are also longitudinal solutions of this. You always were told this, that EM waves are always like that. And what I can tell you is that the most useful ones are actually always like that. But this is only because we excluded some of the things. We cut these out. And that is one reason why we also made some strong assumptions here on the vacuum. This is not true anymore when you have extremely strong damping in this. Then the solution, which I'm showing you here, would be different. So if you have an electric field which is so strongly damped that it actually will decay within the frame of a wavelength, so within 1 or 2, then it actually would also be longitudinal. So your teachers were nice to you because they explained the principles, but they were not fully general. Yeah? Now the question is microwaves which are going down within a wavelength, are they really interesting? And the answer is probably not so relevant for communication or for sensing. Yeah? So the concept which we have here is used, but it's useful, but it's modified. That is what you learn here. Yeah? So this idea is good. Everything is in order. And for example, then if you solve that, you can get, for example, here a simple solution where you have the E field in one direction, second coordinate in the B field, and the third one is actually the line of propagation. And that's a lot already which we got. But there's a couple of things now which will be very useful for these other ideas. And the first thing, and this is now relatively fundamental, that and I really want you to know this. Yeah. So I told you this is not the only solution, but most of the relevant cases for any microwave which we are using are transversal. Yeah? And there's now a unit, a quantity, which is a theoretical concept which is quite wild, but it has two important features which help you. That's why I mentioned them, yeah? Because there's what we call the Poynting vector, which is essentially the vector standing in the line of propagation. Yeah? So this thing which you have always used, this is a specific vector which tells you something about what's happening. Yeah? And what's happening is, as always in physics, you can often deduce from the units. Yeah? And if you just know the very principal thing that the electric field has the unit of volts per meter and the magnetic field has amps per meter, you're coming out with something which has the unit of watts per square meter. Watts per square meter. So this thing which propagates in the propagation of the direction, this thing has a unit of power per area. Power per area. You haven't done anything yet. You have only said there's a vector which has this nature and it propagates. How do I know this? It's just the E cross H. This is exactly what we had as a solution here. And this is the fundamental things, and we don't prove that, but it's fundamentally true for all kinds of waves which are transversal. And it's not only those, there will be more which are also transversal. They look a bit different, but the same idea. Yeah? This is something you need to understand. And the moment you have this, you can already start thinking, what does that mean? That means I'm transporting power through an area. Wow, I'm transporting power. And The next step is then to say, what does that imply? It's energy per time. That's also helpful. But it also means if you have power in the air, you can modulate that power. And that also means in the second strike that you're transporting information, because you can change the amount of power, and that means you can imply information. So it tells you that a wave is really, because it's the solution of a wave equation, is really transporting energy, power, and information. We haven't done much, yeah? But just this S definition is quite useful, just from the units. Yeah? When you now go a bit deeper, you want to calculate the energy density. It's just the same equation. It's a similar idea. It's the scalar products, but it's implied in what's above there. It's just a rewriting. Yeah? So the wave in non-media, that's what you heard before. No, without a medium, that's also this big story about how they found it in the beginning. There's in vacuum, you can transport information, energy, and power. But that's not our problem anymore. Today we are back to how can we transport power, energy, and information in media. So we need to get that back. And we also have to get back these things we cut out. So what we threw away in this foil, this is something I really want to emphasize. When we said this, we threw away all these useful things. Yeah, so we were smashing away all the hardware, all the things we really need to do something. They're all gone. So we have not shown that we can transport something inside the media. Yeah? So we need to get that back into the equation. And now, how do we do this? The first thing is, this is now the link to things we have looked at from a very simple level about 20 minutes ago. Yeah? The first thing is, when you look at this wave description now, is again to look at some units. Very simple. Yeah? So when you, for example, define the ratio of the E and the H, this is volts per meter by amps per meter, which means it's volts over amps. So this has the unit of ohms. And if you recalculate then, maybe already in taking back the simple dielectric constants, which modify isotropically the atmosphere, then you suddenly realize there's two things. There's this, if you just take this solution here, which we took, these E fields and B fields, and fill in some ratios, then you are ending up with because we're using the relation between E and D and B and H, there's always the two factors in between, either the permittivity and the permeability. So the ratio is suddenly defined by the ratio of mu zero and epsilon zero. And you suddenly get a value. Yeah? And this value is actually, if you make some calculations, is 120 pi. And the first learning from this is that nothing has a unit of impedance, or in ohms, and even gets a value. And we haven't done anything. The only thing we said is that without having a waveguide or something in this concept, we have some properties of nothing, which is exactly what we are plotting here. And so this works without any materials. Yeah? And the concept can actually be modified when we are putting in some dielectrics. So isotropically changed gases or whatever, we have a slightly different epsilon, relative epsilon or relative permeability. And there's another reason, and this is now something you have experienced. there's always a discussion, are there typical values for resistors or impedances? And one way you can look at this, that nature gives you 120 pi as a specified impedance, because vacuum, nothing, has this particular impedance in the ratio of the E and the H field. And one thing you can learn from a bit knowledge already, which you have from your daily life, is that for many gases and plastics, the mu is simply staying 1, and the relative permittivity is a finite number, something between 1 and maybe 100. Yeah? So the impedances which nature gives us is given here. You have 377 ohms in the maximum case times 1 over square root of 100, which is about 1/10. Yeah? So that means that nature, without having done much, proposes an impedance level between 377 ohms and maybe a couple of 10 ohms. This is what nature gives us just by the properties. Still in free space, no conductors, nothing. It's just free space transformation. Yeah? Wow. So this you just learned. This is not anything which you wouldn't have known before. It's just looking at it very specifically for the sake to understand what we are doing with this. Yeah? And what is changing, just to be, we have to be more precise, what modifications would be possible. So what is first of all this epsilon correction? It is charging and recharging bipoles in a repeatable way. So you do this constantly. There's no polarization remaining. It's just dynamically changed, and that will cause the this modification of the impedance. And so it's going down, and this is quite homogeneous. And one thing I want to make very clear for air and for the media where we are in, this is useful to be homogeneous. For some components we strongly like that these epsilons are very direction dependent, because we can use them for some devices. So don't exclude that in your head. But for the radiation part, we will just use this nicely. So that's a very fundamental idea. And here, these are some typical values for the epsilon. And you see here, we are typically in the range from 1 to 10, with the big exception is water. Fortunately, the epsilon of water is 81, which helps us greatly in surviving. Also, the atmosphere works because of that. The actual mu here, this is strictly 1 roundabout, and any reasonable component material that we can use these days are in the range from 1 to 10. So the correction in this impedance is something like square root of 10. Yeah? Why do I mention water also? Where's water in this room? You are all water dielectrically. Yeah? So that's important. There's one thing which we haven't talked about, is water has a strong dielectric constant in the real part. So that means in the change of the dielectric. But water also has, we have not talked about attenuation yet. We will take that part in again, but from a different perspective. So at the moment, the media are not damping. So that's also something. This pure atmosphere we are discussing here is not really damping. So this is all going up. And we will insert this attenuation as a correction. That's a fundamental idea. And this is again this idea. Many of the properties we like using is I'm always pretty sure I can reach you up there. So this is long in terms of the wavelengths. That's why the whole story is so similar to these original waves which you got out when you had heard your first optics lectures and so on, when they were explaining that. Yeah? Okay. Now, these corrections, There's one implication which we should mention is that the speed of in the media reduces. Yeah? So the speed of light is defined also by these two constants, mu0 and epsilon0. That's the normal definition of the speed of light. And once we are in media, we will reduce the speed of light. Now you can say, oh, actually this is practically limiting the bandwidth of the internet. Maybe somebody knows that. Why is the dependence of the speed of light also limiting us? Where in the internet do we strongly have problems with that? There's one situation which we all actually like using where this is a big problem. This is when we are sending multiple frequencies over a fiber. Yeah, so we have a fiber, glass fiber, and we send waves through that. And if we need, as some of you know, we need a certain bandwidth, so different frequency to transport information. And the problem is that the left part of the frequencies travels at a slightly different speed than the right part. And if you do this over the Atlantic or over the Indian Ocean or over the Pacific, you can measure that. It's dispersion. Yeah? So the speed, the dependence of the speed of light on the wavelengths through, for example, changes in the material properties is a big problem. We call that dispersion. Yeah? So this is something, because all the nice videos you get, they are not waves as we always account for. So they don't look like that, but they are packages of those. And then if you take that image, you send your video over the Indian Ocean, and the wave package just dissolves. So that the pieces, individual pieces of the information do not arrive in India at the same time, although they were started at the same time here in Germany. That is maybe something which you can already deduce from that. So, now comes the big moment, which is completely non-mathematical, because deriving what is on this foil mathematically is really ugly, really nasty mathematics. We skip that. Now, the moment what you have to assume now is the following. When we now do wave propagation inside dielectrics, we are fine. So when you can understand that if you take a dielectric and calculate the propagation, there's no real problem, because you can do this in gases and dielectrics. The trouble is now, what happens if we now put a boundary by an electric conductor? And there's two cases which pop out of that, which I've only written down. I've not put the equations, because especially the second case is extremely ugly, because you have to solve the full Maxwell equation and they get long. Yeah? So what happens is that there's two findings when you do that. When we now resolve a geometrical case, we are sending this wave, but on the top notch, we let it move along a defined piece of conductor on a printed circuit board. So exactly what you're doing when you're feeding this signal into this board here. This is exactly the moment. So it's clear there's a wave coming, it's put to an antenna and then fed on the board. And there are a couple of things happening at this very moment. And the wave, when going into the antenna, stays a TEM wave. That's very clear. Yeah? Like in the case of the free propagation. And again, when will it stay a TEM wave? I told you that already. The solution is only different if we have strong losses. Yeah? And now you learn something which you might never have thought about. Yeah? in order to transport a wave on a printed circuit board, you need good metals. You need gold, you need copper. Why? Very simple. Because if there were strong losses, when you are feeding this wave in and it lands on the PCB, the moment here there's no change, but if there's a strong change, in the damping especially, then the wave would decay, and then it would also get a longitudinal component, which would be different from what came in. Yeah? And as the metals, we will see that in a minute, have a low loss, they will continue to transpire. So the nature of the wave going into this guided wave is not changed. Yeah? And the losses in relation are bigger. So in a medium, you lose more per length than in free space typically. Yeah, so when you send this in here and it comes out here, there's a significant loss in relation to what happened to the door. That's always something which you have to account for. Yeah? But if you do it right and use good plastics and so on, it's okay. It's not good, but it's okay. Yeah? And but so the wave gets in. Yeah? The other thing is, if we had a very strongly damping material, so the wave is cut when coming into this, but then it would not go much further. Yeah? And then really non-TEM solutions are indeed possible. They are longitudinal electromagnetic waves. It's not a sin to say that, it's true. Yeah? So then this, what you always heard, goes like, it's changing somehow. Yeah? So this, the E and the B field, then also the propagation direction can change. There is also a component then of the E times H in the direction of the propagation. Yeah? When you did your A levels, your physics teacher was always saying, "Don't do that, don't say that." Yeah? That's nonsense. It's not true. It depends on the critical analysis. Yeah? And there's a second thing which is again nice, and I would like to show this. There are more TEM modes which are completely okay due to the inclusion into a resonator. Yeah? So once you have a geometry, you can have more types of waves than we call them modes. They are not just the ones which we had in one direction. There's all kinds of things which are orthogonal to the direction of propagation which fit into the resonator. And I will show you some in a minute. For example, this. Here you have, these are modes where you have the propagation is in this direction, and you can, for example, in a thing, you can have something which looks like a ring. Yeah, so this is the, you see the M field and the E field, or there's also some other modes where you they're completely different from what you learned before, but they're still TEM because as long as the losses are low. Yeah? And the impact of the geometry, because suddenly you have a boundary, is forming these modes. This is the principal understanding what we do there. And if you have seen maybe you have seen something in acoustics, when you analyze a musical instrument, it's the same. So there's also all kinds of waves propagating which are bound to the geometry. Yeah? So everything which fits into the cello, again, it's a nice one to understand this, can propagate as long as the wave equations are fulfilled. Yeah? So this is what happens when we put it guided wave. Yeah, so you define a metal conductor as a waveguide on the top of the dielectric. You get still a TEM wave if the overall attenuation is low, but they look a bit different. But otherwise we are fine. We can still use the Poynting vector to transport the information. Yeah? So that is if we the stronger the losses are, maybe you find a bad plastic, or you put a lot of metal into the plastic, which would be strongly damping then this is getting quasi-TEM. So it's the stronger the losses, the more the longitudinal component goes into this. Okay. So having understood this, now we have directional elements. So we can maybe go back even to a circuit analysis. And now we are going from one view again to another view, which helps us to make this easy, because as engineers, we don't need the fully blown equation all the time. We sometimes just want to simulate this. Yeah. And there's another way when you analyze, for example, now some cable, you come to this description. Yeah? So then you just say, okay, what is my representation of a cable? And then it's quite straightforward. You can do this in 1D, you can do this in 3D, doesn't matter. And then you say essentially in the directional path, you describe it by an inductance per length. And in the parallel path, you do something capacitive. Yeah? So you just say there's a certain capacitance per length. And the only thing what you need for that is simply to say, okay, an inductor in the direction of the component has a magnetic field, so there is some inductance, and the conductor has some capacitance because you are relative to another ground. Yeah? So as long as you have two conductors, this is not really controversial that it works like that. Yeah? And now I talked about losses earlier, and in this simple analysis for the telegraph equation, it's the same. So you put serial losses and parallel losses. This is also not rocket science. What you say with this is when you move along the path, there's a certain resistance per length. And in the parallel path, this is, I have to explain, there's also a certain loss per length. And why is that? These parallel losses we saw already. This is this because I think it's easy to understand. If you have a field and you turn the dipole in this field, you need energy. So with every cycle, this is lost. Yeah. So that means that there's this type of attenuation. And now comes the big moment that you can now take the propagation of this EM wave and express this with a factor of gamma. Gamma is just the argument of the wave, so in time and space, so referring to this. Here we have the solution of the wave equation in free space, which had some kz and omega t, which is both space and time. And we want to relate those solutions with now the electrical way. And the interesting thing is then that you put this gamma, and you can calculate it from two sides now. You calculate it with the wave approach, you get alpha and beta, and you can calculate with the losses per line thing, or inductance per line thing, and capacitance per line thing. And then you look at the same story and you come to this top equation. So these two approaches merge. The other thing which merge is when you run a circuit analysis of this and run the impedance and calculate it, you get this. And the other thing was that in free space we also had the impedance, coming to the same conclusion. So you set these apart. So that means that when you're describing something, a waveguide with a guided wave, these two equations are always true. So we didn't say anything, we didn't say this has to be this specific circuit or this specific cable. They're coming together. And now engineers are smart. If something works for a lot of cases, we say this is a general equation. And we make use of that concept all the time. Yeah? So we would, in this way now, describe anything which propagates a wave by these equations. And so it's the same story. And the reason why we do that is, just to explain that also, is that now, for example, you would, for something you build, so remembering that we take any kind of real conductor, we give it these attributes. And this is exactly what's done in the simulator. So if something has a serious conduction from A to B, we give it this L dash on this C dash. Yeah? So, and this is what's run in the background when you when you make a simulation for how much attenuation do I get for this particular component. Yeah? So that's, and it's for a wave. It's not for just electric currents. Yeah? And there's a distinction now, which I would just like to remind you. For optics, you have seen this. There's a small difference now. So for optics, you have seen guided waves, for example, the fiber. The fiber was always told you in the following way. So when we have optics, there's dielectrics, which is, we have different dielectric constants, especially those at the boundary. So vacuum is always 1, and if you have a higher dielectric constant, you get a change here at going to vacuum, or even a change between two materials. So essentially the same. Yeah. And how does the fiber work? It uses this Snell's law, and also the idea that at some angle there will be a total reflection of the optical wave. Yeah, so if you can go from one material to another, but if you are inside the higher dielectric constant material, then there will be, at some angle, if you do it right, there will be only total reflection, keeping the signal inside the material with the higher dielectric constant. And that's why a fiber works, because if you obey this angle, you're going zigzagging through the fiber, and surprisingly the internet works. Yeah, so that's the idea of a fiber. What we do now is something very similar. This is here the total reflection, so you may see it. So there's some specific angle. If you're too steep, it goes still through. If you are flat, here we have now the guidance not only on the interface, but here we have the guidance now with the metals. So this is the critical thing. So the metals say where the wave will flow, forming this resonator. That's the change. Yeah? So there's a distinction. And now what would transpire there? This is now what I was talking about. This is now the solution of this wave in this case. So you get a wave on top with an amplitude, and you get two terms: the gamma, which is the term for the space, and the timing one. And you get there's two parts now. The I beta is the one which is the oscillating part without attenuation, and the alpha is the attenuation. Yeah, so it's a function which has an exponential function. There's a decaying part, which is this alpha, here compiled in this beta. This is the first part, and this is the space part, which just moves over space, which makes it a wave. And this is so related to these circuit parameters. Yeah? So the alpha is the attenuation factor, and the beta, we call it the phase factor. Yeah? So and the good thing is about this, it's a guided thing, and it works as if it was running in a cable, whatever it is. So it's not necessarily bound to something like that. It's anything which would transform a guided wave in this. Yeah? And you remember, even free space has an impedance, so we don't need that guidance. So, but if it's guided, it still also has an impedance. This is a way to read it. Yeah? So we have waves in the materials. What is now interesting is to put it to the real world. Yeah? So how are we now defining these alpha terms, especially? Because then we have to look through some real facts. What is now changing? Yeah? So what is, for example, defining a transmission line? Here we have an example. A transmission line. Top is just a waveguide where we put a piece of metal on a dielectric, and underneath we have a ground. That's a very famous example, which we more or less do automatically. And to explain now how this works, this is a coplanar one, which is the other type. And what I'm pointing to, so for example, the coplanar one is the ground. This is the ground, and this is the signal line. This is nicer because you only have to do it on one side. Yeah, and what are we now interested in? For example, to learn about the attenuation. And where can you see the attenuation here? Obviously, you're seeing a structure. Yeah. What is the brown stuff and what is the yellow stuff? What would you guess? What is this? They're both gold, pure gold. The only difference is that the brown stuff is it's done in a different way, and it's much rougher. Yeah, so the yellow gold is extremely smooth because it's sputtered. And the brown gold, which optically looks very different, it's the same material, is galvanic gold, which is way rougher, and that's why it looks brownish. Yeah? And what I'm trying to imply here is, so it's not only the material which is counting. Yeah? And you could look at these mechanisms now. So you have now these waves in the dielectric, and on top you have now a metal. Yeah? And this metal in itself has a property, but it also has a surface. Yeah? And it is somehow clear that in the yellow case and in the brown case, we have different properties. You see that already optically. But so if it's from a reflectance different, maybe it's also different for the wave. And the answer is yes, it is. So what we are now asking for is, in order to understand what's really happening for us, is we are trying to find values for alpha, for this attenuation. Yeah? And this is quite straightforward. It's something which is really something you can do. So for example, there's now individual contributions to this damping. Yeah? And one thing is something very simple. It's just a serial conduction loss. And this is simply a resistance. Yeah, so this is really what you know as resistance. To be a bit careful because a lot of things happen, but first thing is there's a resistance in the metal which contributes to loss. Yeah, because what is induced in these structures, in the waveguides, it is currents and they flow. And they observe a certain resistance which dissipates power. Yeah? And the dielectric loss tangent is also there, this is the parallel loss through the substrate, because for any waveguide, some of this, there will be some field here in the substrate. We still have to talk, we will start again next time again with this, but you still have to see how much of the field is really in the substrate in this case and how much is outside, because here there's nothing and here there's a dielectric. So the field distribution will be critical, but just for some waveguides we might get some values for this parallel loss. Yeah? And then we might also have some parallel conduction losses. So in case the plastic is not really an isolator, but it's a bad one, which has then there will another contribution, and you simply give than the loss in dB per meter. So what do you lose? So that's what we have. Then there's the losses due to the radiation in this case, and this is always overestimated. Many people say, oh, this is radiating. If you're really looking at it, it's very seldom radiating. That's something which we typically can forget. And there are also some effects which are now very specifically wave. Yeah? So they are, for example, some of the losses are frequency dependent. Yeah? And the surprising thing is that these serial metal losses, they have a frequency dependence, but it's not linear, but it's a square root. Yeah? Then there is just in comparison some things which are easy to be understood. So that's something which I really like. If you have dielectric losses, they are directly proportional to F. And that's very simple, because if you have a higher frequency, you change the dipole many more times. And if you go higher in the frequency, it's going higher. Yeah? So that means it's proportional to F. Yeah? And then there are some a bit spooky things, which there's one effect which is straightforward, which you know, which is the skin effect, which has to do with the RF. That is, if we are sending a current through a metal and increase the frequency, then the field distribution in the metal, the higher we go in frequency, will more and more move to the skin. Yeah? So inside the metal there will be less current, and it will go outside because the fields are interacting and pushing themselves out. That's the idea. Why is this important? It has two fundamental consequences. First of all is the diameter of the effective diameter of this is reduced. And this is now very interesting. Why? Because you know that the diameter defines the power capability. So if you have a strong, in any electronics, if you have a big power, you have a big cable. Obvious. Yeah? The trouble is in RF we also have that, but the fields are, even if we have such a diameter, we lose the center because the fields are moving outside. They're reducing the diameter. So you sometimes really have to check whether is there too much current per area, because otherwise the whole thing will blow. So if you build a radar and don't observe this, then you blow your radar. So just as an idea. And the second part is, and that's why I showed you this here, gold and gold with different surfaces. If you have a rough surface, this will also increase the attenuation. So we're finding a surface correction factor that we say, there's even a model. So you say, because of the roughness of the material, RMS is a measure of roughness, or how rough is something, and you get even the attenuation because there's roughness. The higher the roughness, the higher the loss. Yeah? And you see, this is particularly critical because the skin effect pushes the fields towards the surface. So that's why we are, and many people who are doing semiconductors, they're always polishing to keep very good metals, yeah? Flat metals. But this is all. So we can deal with these things. They're a bit spooky, skin effect, roughness, but there's not much more. Once you have these ideas and know how it works, you can do these things. You can send waves. You describe the waveguides with these R, L, and C parameters in our model, telling you how much attenuation you have. And then what you flavor in are the material parameters. Which metals, which conductivities, which dielectric constants, and which attenuation levels do you have. And with this, you can then start to design wave-based circuits. So it's not so different from what you might have done before when you were just connecting the components. So it's So the critical summary is this. Left part was calculated from the wave side. Right part was calculated from something which looks like a circuit. Somehow they go together, and the equivalence of this is helpful. What is nice, you don't need a circuit to have an impedance. Free space works like a circuit in a way, but a circuit also works like free space. This is what HKT is saying. And the physics is also not violated. As I said, there are some things which we sometimes look at, but we mostly don't need them for as long as we are in what we call the far field, far away from this, in the free space. We call that if we are many wavelengths away from the antenna, we call that far field. On the chip, we have so little damping that the signal stays after a couple of hundred or whatever propagation steps, so to say. Pooh, a lot of ground covered. Are you happy with this? Is this understandable? Does it make sense? It's a mixture of, we are sneaking around mathematical equations, so we omit the ugly ones, but we are sure we are right because the materials we use are okay. Yeah? And for some special things, for example, there are some of you have seen this already, for example, something like an isolator, just to say where this concept does not work. So these omissions we did here, they will not work for all components, but for example, for an isolator, they don't work because there we definitely have a magnetization. So there we put a strong magnet into the component. But the trick is, I really have to go to the beginning. So we have in some memories we have polarization, and in some special components we have a magnetization. But then it's only for this component that we have to consider this, but not for the rest. And that's why it's working. Yeah? So just to give you a flavor why this might be useful. Yeah? So we are not omitting this completely, but when we then look at one component and think about how we deal with that, but otherwise the cases which you knew already works more or less. Yeah, so pooh. Questions? Any comments? Where do you feel unhappy? There was one thing which I left out. What is so the product of frequency and wavelengths is the speed of light. If the speed of light goes down, which part is going down then on the other side? Wavelength or frequency? Yeah. So this is some part which I really would like to point to. So if the incoming wave in the free space has a wavelength, so it has a frequency of 3 gigahertz and a wavelength to this point of 10 centimeters. If it enters the chip, it has a frequency of 3 gigahertz, and the wavelength is corrected by the square root of epsilon. So if you have an epsilon of 10, you have a square root of 10 lower wavelengths. So in the chip, the wavelength is only 3 centimeters. And I think I said that also in the intro. That's why Telecom, Indian Telecom, German Telecom buys frequencies, because they're unique. Yeah, so frequencies are always the same. Speed is modified by the dielectrics. Wavelength goes down. Okay, then no further comments, no further questions. And I hope I could link some things newly from your experience to physics, which you already knew about. Nothing bad has happened. It just explains why it's working. And we don't look at tensors. Typically, we do simulators work that for us. So, for example, when we, instead of looking at this, this is why we do this in the design course, we never look at this. We always turn on momentum or a 3D simulator like EM Pro. Yeah? So this is why, because you never want to really do the calculation, because the geometries are so complicated that we typically say, have the simulator do that. And this is also why this automation of the flow is so important, because nobody wants to go do a single-ended tensor, but we want, where is this? I ran over it, sorry. Here. This is why we want this one-to-one between schematics and geometry, because if we can move between the simulator, that's equivalent of not having to touch any tensor. It's just you transport it from one program to the other, and don't do any real calculation. You just give properties to a simulator and run it. That is the fundamental idea why we have this design course. Yeah, nobody has to go to a piece of paper and run a calculation. Okay? So then, looking forward, and thank you very much.